Okay, so I realized that you know, the problem I gave about I'm still thinking about this problem that I gave about finding this parameterized family of Morse functions on the surface, but I realized that if you're having any trouble at all, I'm sorry, I forget your name. Nick. I was talking to Nick about this, and I realized, well, I'll draw the same picture again, but make it a different problem, right? So I'll draw this picture, but now I'm talking about a circle embedded in R2, right? Just as a warm up, it's even easier, right? But you know, it's also worth doing. So if you draw, you know, well, let me call it sigma again. Okay. But now sigma is a embedding of S1 in R2, and you can do exactly the same thing. You can consider different directions, right? You can put in a random direction, V, and you can project that curve onto the line given by the direction V, and so you still get f sub V from sigma to R, but now V is you know, this function is parameterized by the circle. Okay, so if you want a warm-up problem, do exactly the same thing for this, and it's just a little easier to draw the picture because we want to draw the critical values, right? Values inside in S1 cross R, and so you draw S1 cross R as an annulus, and you know, just to get started, when V points up, which is going to be here, you have two critical values, right? And your index 0 and index 1. When V is horizontal, again, you have 6 critical values, right? And there are various indices. Index, I guess you'll have 0, you have 2 index 0 critical values, and then index 1 critical value, and then index 0 critical value, and then 2 index 1 critical values, like that. So as you move around the circle, so this just gets you warmed up, right? Something happens somewhere when you're turning, and it's a little, Nick and I were talking, it's like, it's not totally trivial to see where it happens. You know, you don't jump immediately from 2 to 6. You go from 2 to 4 and then to 6. And is it these two that show up first? Is it these two that come, you know, are these born together or are these born together? Which ones are born? The other thing that will happen is you'll have crossing. Some critical, once you have 2 index 1 critical points, maybe one's above the other and then one drops. So the sort of the events that we're interested in, the events are births and deaths of pairs, right? Births, deaths of pairs of critical points. And the other event will be, so that's one, the other event is crossings. Crossings in this picture, so there's changes of 2 different critical points. They stay far away in the domain, but their values shift, so one becomes higher than the other, right? Crossings, so change, crossing, you figure it out. So that would be some sort of, we have maybe this would come along and they switch heights. One would be higher than the other. So that's I mean, this already is an interesting problem, and so we should start with that. Okay, so where were we? We were trying to prove that the goal, right now what we're trying to prove is a little dilemma, which says that if X is a cobordism from M0 M1, and when I say COB stands for cobordism, and by the way, why is it called a cobordism? Well, board is the French word for to bound, okay? X is not the boundary of M0 and M1, M0 are the boundaries of X. So X is the co-boundary of M0 and M1. That's the sense. That's why it's got a co in it. So if X is, and also for me, cobordisms are always compact. Okay, we don't want anything weird happening, some weird holes in the middle of it or anything. So everything's really compact unless, I mean, that's it. I said at the beginning everything's smooth, probably everything's compact unless stated otherwise. And so if X is a cobordism and F is a smooth function from X to 0, 1 with the usual convention, so it's a Morse function on it. So in other words, F inverse of 0 is M0, F inverse of 1 is M1. And if F has no critical points, then we want to conclude this is the this is going to be the first example of going from a knowing something about the Morse function to knowing something about the topology of the manifold. Then X is diffeomorphic to 0, 1 cross 0. And if you want, you can be even more careful about it. The diffeomorphism we construct will be such that the Morse function on F becomes, under this diffeomorphism, just projection to 0, 1. But that won't work. So the proof, first of all, the outline of the proof was that we're going to say, okay, here's this funny looking manifold, cobordism. Looks like, and what we want to do is construct a vector field. So construct a vector field V on X such that df of V is equal to 1. It's constantly equal to 1 everywhere. And what that means is that it points up in, this is mapping to the interval. This is mapping by F to the interval 0 to 1. And then from my vector field everywhere, it projects to a unit length vector here. Actually, really the vector is long, right? It's unit length. But the point is then, what we're going to do is we're just going to, and we'll come back to this, we're just going to start at, the diffeomorphism we're going to construct is actually going to go from 0, 1 cross M0 into, we're going to go construct the diffeomorphism this way. And so if I want to know if I have a point here, P, and I have a real number T, then where does T comma P go? It'll go to the place you get to by starting at P and flowing along the vector field V for time T. And that'll be diffeomorphism. So, but let's talk about why this vector field exists, and to do why that vector field exists, there are several different ways. They all involve partition of unity, but I kind of want to do the most general way, since some of you may not have seen this before, which is using a Romanian metric. It's sort of overkill for this thing, but let's just do it anyway. So I wrote down the definition of Romanian metric, sort of. The smoothness is what I glossed over, but let me just remind you again, Romanian metric means, so at each point, Romanian metric on X means at each point P and X, you have an inner product, G sub P, is an inner product of T, Tx plus Tpx to R. So a positive, definite, symmetric bilinear form, symmetric bilinear form, so positive, in local coordinates, it's just a positive, definite, symmetric matrix. And then varying smoothly in local coordinates. Varying smoothly with P just means, when you write it down in local coordinates, every coefficient of that matrix is a function of your position, and those functions should be smooth in the local coordinates. So the first thing is claim X has, whatever X is, it has a Romanian metric. And the way you produce this is as follows. So you're just going to do, I'm just going to sketch this. It's a partition of unity argument. So the proof of the claim is cover X with coordinate charts. I don't know what the right term is. Coordinate charts with a partition of unity. If they're small enough charts, then there's a partition of unity associated to it. Remember, a partition of unity is a collection of functions such that locally, at most finitely, many of them are non-zero, and the sum of them at each point is 1. Okay? It's a smooth function. And then they're subordinate to this, they're associated to these coordinate charts in the sense that their supports are inside these coordinate charts. And so then you, in each chart, chart, UI, you choose the standard, let G sub I be the standard inner product in these coordinates. In other words, to be very technical, you take the standard inner product on Rn, U sub I comes with a diffeomorphism. There's a diffeomorphism from U sub I to Rn from this coordinate chart, and G sub, and then you pull back this inner product there. Do I need to say more about that? So now all I want to say is patch these together with patch these together with unity. Okay, so what does that mean? So that just means, so the partition, you have some indexing set for your coordinates, and you have let's call our partition of unity U sub I. It's going to be from X R. So for each I in the indexing set, you have this function U sub I, this partition of unity, and you let G equal the sum of U sub I times G sub I. So that's just saying at each point, if you have two vectors and you want to take G of V and W, G of V sub V and comma W is, mu1 times G1 of VW and so on. And so all you have to check is that a convex combination of, so convex combination means you multiply, you have a whole bunch of things, you add them together, multiplied by some numbers that add up to 1. Okay? So you have to check that a convex combination of positive definite symmetric matrices is a positive definite symmetric matrix. Okay? Clearly, any linear combination of symmetric matrices is symmetric, and the positive definiteness requires that they add up to 1, right? So check that convex combinations symmetric matrices are positive definite symmetric matrices. And the symmetric is trivial and the positive definite is only slightly less trivial. Just do the basic case. If you take, the simplest combination is t times g0 plus 1 minus t times g1. Anyway, your positive definite is just that if you take a single vector, g0 of uu is positive, right? If u is not 0, so t times g0 of uu plus 1 minus t times g1 of uu. If these two things are positive and t and 1 minus t are positive, the whole point is just a positive combination. So the coefficients are always positive, and so that's going to be positive. Any questions? So Riemannian metrics are relatively easy to construct if you believe in partitions. But why Riemannian metric? What we want to use a Riemannian metric for is to get this vector field. And the vector field is going to be a gradient vector field. So given V now, we get V as follows. And so we've got F mapping X, right? So how do you think about an inner product? Or what's a good way to think about an inner product on a vector space, right? It's a good way to think of it as an isomorphism between the vector space and its dual, right? So for each p, you can think of G sub p as a linear map from the tangent space of X to the cotangent space of X, right? Where if you take the vector v, you map it to the covector, you map it to the covector, which is G sub p of v, comma, maybe second space blank, dot. Questions on what that means? The standard construction, and then the property of being inner product guarantees that this is an isomorphism. And so it's an isomorphism, and then now given your function f from x to 0, 1, you get the differential of it, df. Df at a point p is an element of the cotangent bundle of x. Okay, and so that we're going to use, so I get an element of the cotangent bundle, and you take gp and let v. I'm trying to construct a vector field, so I'll define it at each point, and let vp equal df at p inverse, g at p inverse. And that's the whole point of doing this, rather than just saying, well, at each point pick some random vector that's perpendicular to the level sets that maps to 1, is that, that's just good things. You don't get smoothness that way, right? But this since everything's smooth in local coordinates, everything will be smooth. Smooth. And actually, I'm sorry, I'm not quite done. Let's call that W. I need to rescale it. Just a minute. I'm not done. Because I want to have like 1 with respect to df. So the first thing I need to know is that, right, so how are we going to use the no critical points, right? Because f has no critical points, df at p is not 0, therefore w at p is not 0. Okay, so it's a non-zero vector. But more important than that, I guess, is so what is? Well, let's figure this out now. What is df at p of w? Okay, this is slightly confusing, but the important thing is that so the claim is this is the same thing as gp of wt. Okay, so why is that? gp of wp. Stop saying the p's. Okay. G of w, right, should be, w is mapped to g of w comma something, right, as one form. And if w is mapped to the one form df, then df of w is g of w. That's all it is. So then, and then the fact that this is positive definite means that and the fact that this is positive definite and this is non-zero means that this is positive. So that's a function. It's a smooth positive function, and finally we can therefore let v equal 1 over g of ww. And so we can as long as it's non-zero, we can rescale it to have. I'm not saying it has length 1. I'm saying it projects to a vector length 1. And then df of v is questions? So finally, to now construct phi 0, 1 cross 0 to w to x by phi of cp equals, now I don't want to, notation regarding flows can be really horrendous. And so I'm going to, if I just say equals the point you get to, this is worse than the notation story because it's a whole lot of words, but a whole lot of chalk, but the point you get to by starting at p, just get the picture up here again. And so we're kind of constructing a map from the product to this thing. So if I have a point here at height t and p, this is height t and this is point p, right? Then I'm going to start here at point p. This is m0 down here. This is m0. I'm going to start at the point p, and then I'm going to flow forward along v. Who knows where it goes? Maybe it should get to the same height. There, and this is p. So what do I need to know? I need to know this is diffeomorphism. And the, sort of the general stuff about flows will tell you that this is a smooth map. And so I want to check that it's, so let's see, how do we know that it's invertible? Okay, I mean, how do I know that I don't get to, what am I trying to say? Yeah, I mean, I want to know that it's that I don't have two different points mapping the same point. That's existence and uniqueness of solutions to ODEs, right? If I started somewhere else and in the same amount of time I got to the same point, then I could start at this point and flow backwards and have a contradiction, right? Because you can flow, you can flow forwards and backwards. Okay? Basically, because of backwards flows, that's never going to happen. And you don't get to the same point at two different times because it doesn't cycle back, right? Because it's always going up. And then lastly, you want to know that you actually get everywhere and then you get out. So to know that you get everywhere, if you want to know how do I get to just flow backwards, right? If I want to know that I can get to a certain point here, well, I've got the vector field and I flow backwards, and I know that the point is I know that in finite time, less than 1, I will get back to here because of the fact that df of v is constantly equal to 1. If you want to be very formal about it, you say, well, anytime I'm flowing here, I'm also mapping to 0, 1, and so if I start here, I can just flow with respect to the unit vector back in 0, 1. And if I take p and I start here, and I take p and I flow forwards for time t, then I can look at its image, and its image will be moving up with constant speed, right? So its image is always going to get at the top, and if I start anywhere here and I flow backwards, I eventually get back to the level 0, and so I get everywhere. So this is a different one. So that's I could belabor that point more, but I think everyone okay with that argument?
So there's only two places where you have to use the fact that there are no critical points, and this is one of them, right? For the uniqueness.
Well, yeah, in some sense, I mean, once I've got that df of, yeah, once I've got this though, I mean, really, yeah, what I want to, if there was a critical point, right, then you'd never get there, right? If there was, that's sort of a good thing to observe. If you have a critical point, then this vector field, which is what's the generalized gradient vector field, right? By the way, it's worth also going back and checking, if you haven't never done this before, that if you take the standard inner product on Rn and take an ordinary function of n variables and do the ordinary gradient as in multivariable calculus, you get exactly this, because it's exactly what the ordinary gradient is. Okay? So, and the ordinary gradient will be 0, but anyway, if df is 0, then w will be 0, so if you have a point where the vector field is 0, then you'll never get there by flowing. How do you know you never get there? Well, if you start there, you never leave. Again, it's the forwards and backwards thing. So since starting there you never leave, then flowing forwards there, you never get there. So that's kind of what okay, so that was our first thing. And this is there's a famous theorem called the HCoordinate Theorem. I'll just mention it briefly. I'm not going to give the full statement of it, partly because I can't remember it exactly. The HCoordinate Theorem to Snail, and it says that it says suppose you have a coordinate of sufficiently high dimension, and I think it works easiest at dimension 7 or higher or something, right? if you have a coordinate with sufficiently high dimension, and I think you need that it's simply connected. Okay. So this is x is n is bigger than or equal to 7, I think, and maybe something. There's some extra things you could do to make it work at 6. If I1 of x is 0, and if, I'm going to say this, if x looks like a product from the point of view of algebraic topology. So that just says that, that means that if anything you could possibly compute and using algebraic topology, homotopy type, etc. I mean, there may be there's a cleaner statement of this, but this is my simplistic understanding. Up to any algebraic computations, relative homology, relative ends, and so on, it behaves just as if it was manifold cross interval. Then it actually is. Then x is a product. I'm being very vague about this, but this is how you prove the higher dimensional Poincare conjecture, which says that if you have two manifolds that are diffeomorphic to a sphere, then you can argue that there exists an H-cobordism between them. An H-cobordism is a cobordism that is up to homotopy like a product, is what I'm saying. So there exists a cobordism between them that looks algebraic topologically like a product. And once you know there exists a cobordism between the algebraic topologically like a product, you can conclude that it is a product, which means that this is, well, there's the question of diffeomorphic versus homeomorphic I don't want to get into, but that's more or less the idea. You actually end up only concluding this is homeomorphic to that. But that's just an example. So the proof goes about constructing a Morse function on here, using the algebraic topology to eliminate critical points, and saying because of the algebraic topology, you can eventually get a cobordism that has no critical points, and therefore it's a product. And then that whole question of how you use the algebraic information to show you can get rid of critical points, and you get rid of them by forcing them to cancel in exactly this kind of way that we're seeing with more parameterized families of Morse functions. So you kind of pair them off. Okay, so good. So now what if there are critical points? So let's do the simplest case where there's one critical point, right? We said no critical points, let's do one. So suppose I have f, again, x is a cobordism, 0 to 1, and f maps x to 0, 1 has a single in Morse, it's a Morse function, and as a single critical point. What can we say about the topology? We want to know what can we say about the topology of x. This is I want to use a vector field again, try to think about it, but now we're going to think about what happens at the origin, at the critical point as well. But before we do that, I want to, so I could just pick a random Romanian metric, again take its gradient field, vector field, and then see what happens if I flow along it. One of the problems with that is that a random metric near that critical point, its gradient vector field could be pretty weird. But we already know that it's a Morse function, so it has particularly nice standard coordinates near that critical point. So what I want to do is I want to choose a Romanian metric on X such that, let's call this critical point P, P X, such that, let's call this Romanian metric G, near P, there's this coordinates, how about I say that if this coordinates x1 to 10, with respect to which one, f is the standard, let me start like this, sum of plus or minus xi squared. Now the standard Morse function we wrote down. So it's a good coordinate system for the Morse theory, right? And the second thing is that G is the standard Euclidean in those coordinates. So in other words, dot product of d by dxi, d by dxj is delta ij. And so I'll show you the question of why can you do this. It's not hard either, but before I do that, because everyone understand what I'm asking for. So I'm asking that it's kind of special. In fact, if you've never thought about Riemannian metrics before, you might think, isn't every Riemannian metric locally look like the standard Euclidean dot product, right? Well, at a point, it does. So in the tangent space of a single point, you can always find coordinates, because you can diagonalize the matrix, you can always find coordinates so that it looks like the standard dot product. But I mean, this is not the subject of this course, but you can never, you cannot in general expect to find a coordinate system so that in an actual coordinate neighborhood of the point, everywhere it has that product because of curvature. And so that's the subject of Riemannian geometry. There are invariants that prevent you from there are invariants called curvature that prevent you from finding such coordinates precisely. And so, on a sphere, you cannot find a little coordinate patch in which it looks like a normal Euclidean inner product, or a sphere would be flat. And so, what we're sort of saying is we want to force it to be flat, metrically flat, near those critical points. Okay, so why do such things exist? Existence. Well, all you have to do is you use step one is choose coordinate charts. So cover X with coordinate charts such that each critical point, well, there's only one critical point, but you could do this in general as well. Many critical points for any Morse function is in exactly one chart. Okay. You can never arrange each point in the whole manifold is in exactly one chart, but if you have a favorite point, you can arrange that there's only one chart that works for that favorite point, right? So if there are other charts that contain that point, you just change it like that. You want that point to be only one chart. Okay. And that chart is, and F is standard in that chart. So it's a nice Morse local model in that chart. And once you've done that, then you use partition of unity to construct G. This partition of unity for this particular coordinate covered by coordinate charts. Okay, and then automatically in a very small since P is in only one of these things, and the small neighborhood P will be in only one of those, you force it to be flat.
That point one seems more. There's quite a lot involved in that, right? Because to get it in that standard form of the plus minus xi squared, you just know that there exists some coordinate chart around it.
Okay, so cover the whole manifold with, you know, maximal atlas or something, right? And so one of them will be this. How about this? No, maybe pick a locally finite coordinates atlas. Okay, so cover with lots of coordinate charts, and then on top of that, throw in the standard chart for each one. Right. So I've got a random locally finite atlas, plus I've thrown in the Morse standard charts. Okay, so now it's still locally finite because I'm only throwing in just at each point I've thrown in a small one. Right. Now I want to go back and then I think there's some process to go back and at that. Well, yeah, just at that point I can look at all my charts, and domains of charts in principle don't have to be balls, right? So I can just delete a small epsilon neighborhood of that point from the domains of all the charts except that one, and then all the charts automatically have divide that.
So is it special with the fact that there's only one critical point?
No, actually, well, what's important is that critical points are isolated, actually. And so isolated means, the set of critical points is a closed set. And how do we know that critical points are isolated from Morse functions? Well, we have, again, I've sort of pushed a whole bunch of stuff under the rug that I want to talk about later, but once you believe Morse functions exist, they're just, my definition, just in terms of local models. And in any local model, there's only one critical point, right?
So I guess I'm curious.
And every critical point has an open neighborhood that contains no other critical points.
So if your critical points are isolated, then you can construct a locally flat.
You construct a metric that is locally flat near the critical point. Elsewhere in the manifold, who knows what happens.
Okay.
You're just forcing it to be flat right near those critical points.
Okay.
It's kind of weird. It's actually it's sort of intellectually obnoxious to have to do that, right? But if you start thinking about all possible metrics, well, you'll see what we want to see what happens. So what do I want to do with that? So once I get this. So now let W equal, let's write G inverse of df. Again, so that's the, sometimes this is written grad sub G of f. Right, the usual, so this means the gradient, this is a definition of this symbol, the gradient of f with respect to the metric G. Okay? And the point is that near P, we know exactly what, near this critical point P, we know exactly what W looks like. W is equal to the ordinary Euclidean gradient. Okay, this is the exercise I said you should do. You should believe me that if you take the ordinary in the product and the ordinary, and then the ordinary Euclidean in the product, then this thing gives you precisely the standard gradient. So I've got f equals minus x1 squared minus k squared plus xk plus 1 squared plus xn squared. Okay, so then w is going to be precisely minus 2x1 divided by x1 minus 2xk divided by xk plus 2x plus 1 plus 1. Near that. And so it's going to, we're going to think about the flows in there, and okay, so let me draw kind of a schematic picture of what's happening here, and well, I'll draw actually this is sort of a realistic example. Realistic examples have the danger of getting you to believe things not always true. But so this is an example of a surface, which is a cobordism from M0, which is a single circle, to M1, which is a disjoint of two circles, and there's a single saddle. Here's one, there's our point P, there's our P. Okay. Now, by the way, the flatness, you can't read, you can't see the metric here. It's hard to sort of make this flat, and that's the Morse function there. Now we should have given a name to our, so everything's, so G, F, and W are all going to be then standard in some neighborhood. Okay, so U is this neighborhood of P. All right, so what I want to do is I want to draw a picture of this coordinate neighborhood U first. Right, so local picture. I want to draw a different kind of picture of U. Local picture of U. And what's happening inside of U. And so it just looks like. Well, the picture I like to draw is I like to draw the x coordinate is going to be x1 up to xk, and then the y-axis is xk plus 1 up to xn. And so in this case, this is this direction. This is xk plus 1 xn. Those are the directions in which the function is increasing, and then that's x1 and x2. So here's my coordinate chart U. And now I want to draw the level sets of the function and the gradient-like vector field. And so the level sets of the function are when the function is 0. Yeah, I mean actually. Remember, f of p is not 0 here, but then I choose local coordinates so it is 0. So let's just sort of reshift things so we think about 0 just to make it simple, right? So the inverse image of 0, or the inverse image of the critical value, is going to be something like this. I'll show the colors there. Okay. And so this is f inverse of. Well, let's see, this is f inverse of f of p. And then because that's when sum of the xi squareds equals the sum of the these other squares. And then if I look at when it's less than that, say f of p minus epsilon, I kind of do something like this. And this is f inverse of. Yes. So this stuff together is f inverse of f of p minus some epsilon, just below there, right? Because how do I know whether it's below or above? I mean, I know just from this general formula sum of squares that it's going to be hyperboloids, right? And then how do I know which one's positive, which one's negative? Well, along here, these coordinates are 0, these coordinates are non-zero. So the sum of these squares is positive here, and I've got those have negative signs in it, so this has got to be the negative one. Okay? And then I go up here, and the other hyperboloid I have is going to be that together, and schematically this is f inverse of f of p plus epsilon. And now what does the vector field look like? Vector field is, that's the other thing that's sort of, you should check if you've never done this before for this gradient-like vector, for a gradient vector field for any metric, the other condition that you have is that it automatically follows, even if it's not the standard Euclidean metric, is that the gradients are perpendicular to the level sets. Okay? And that's also easy to check. But anyway, here it's completely standard, so I can draw the flow lines for the gradient vector field, and in particular, flow lines when they go up. By the way, why did I not divide this by its length? Well, the problem is that right here, the gradient really is 0 again, so I can't, I'm going to eventually try to renormalize things to have like 1 in some sense, but I have to do it away from here. And so in particular, if you think about this, if you start it at this level set just below f of p, and you want to flow to this level set just above f of p, if you're over here, it takes some amount of time to get there. If you start really close to this axis and you flow, it's going to take much longer because the vector field is getting very close to 0 here. And because the vector field is getting 0, you spend a lot of time. So if you start really close to this x-axis and flow here, you kind of get, you spend like your lifetime here before you finally zoom out of the way, right? And of course, if you start right on the x-axis and flow, in some sense, I mean, you never get here, but that's your destination, right? And you stay okay, so what I want to do is I want to decompose this manifold into several different pieces. Okay, I think I'm going to end without far from finishing this story. So let me just tell you the outline. I want to decompose this manifold into something that I want to go up to a certain level, so that that level set comes into this picture. Okay, so I'm going to go. Manifold's going to. I guess I'm going to break it into I'm going to break it into 4 pieces. Okay, I'm going to break it into one piece, which is everything up to a certain level, so that level is very close to the critical point. And then I'm also going to go everything above something just above that critical point, right? And then inside here, I'm going to break it into one part, which is let me schematically draw it. One part which is going to look like this. Okay, so it's going to be, remember, this here, that's F inverse of F of P minus epsilon. Okay, and this little bit of it there is what we're seeing here. Okay, and then I'm going to take that little bit and look at everything I get by flowing forward until I hit F inverse of F of P plus epsilon. Okay, plus, well, of course, if I look at everything I get by starting at this set and flowing forward, right? What will I get? In this picture, I'll certainly get all this stuff flowing forward until I hit here, but I won't actually get any of these points. Right? But if I take the closure of all the stuff I get by starting here and flowing forward as far as possible until I hit FP, I'll also include this point here in this axis. Okay? So that's this piece that I'm going to pick out in the middle, which somehow is going to sit in here. Somehow like it's going to be sort of sitting right there over the critical point. And then outside that piece, I'm just going to be able to, I'm going to take this intermediate levels here, but I'm going to ignore this. And outside this, I can rescale. I'm inside this set here, I'm going to do something special. Outside that set, I'm going to rescale this gradient vector field so it has length 1 as normal, right? And then I can flow from here to here in time 1, or in time 2 epsilon, right? Flow from minus epsilon to plus epsilon in time 2 epsilon. So this stuff here, which is extending all the way out here, will just look like a product, as usual. But it'll be a product kind of with this funny corner on it. So the whole thing is going to break into 4 pieces. A product, because there's no critical points, right? And then sort of a product, but there's a little bit removed from the middle, and a product up here. And then the special little bit in here we'll analyze in detail, but it's this thing, and it's going to correspond to what's called a handle. Okay? And so then we'll get what's called handle decomposition. There are other ways to do it where this thing doesn't have these funny corners, and I'll talk about those various different ways to do it.